This is my submission to 6002X CECC4, combining op-amps with vacuum tubes to build an audio amplifier for guitar or hi-fi applications. I'm Dave Meggs, and you may know me as DC Meggs from the discussion board. I would like to discuss audio amplifiers, particularly vacuum tube topology known as push-pull, and look at integrating solid-state components into those designs and attempt to mix modern components with those of 50 years ago. I hope to take about 5 minutes to give you an explanation of the topography of the circuit. Then I'll show you a few examples of common tubes. I'll show you a typical VI curve for a small signal triode known as a characteristic curve, and I'll show you how similar it is to a MOSFET. Then we'll use that knowledge to analyze the characteristic curves for the push-pull design, which is a bit different. Then with that background, we'll dive into the circuit I've built for the contest submission. Then I'll connect it up and we'll look at it on the scope and see how it looks and see how it sounds. That will take at least 30 minutes, which is about as long as I should impose, but if you want to stay around for extra endings, I'll discuss how this relates to guitar amplification and the changes that we must make to the circuit for that application. I want to show you a typical output stage from a push-pull amplifier. At the heart of this circuit are a pair of pentodes, and they operate 180 degrees out of phase with each other across the primaries of this winding. Our high tension or B plus voltage from our power supply is connected here to the center tap of this transformer, and the large signal current is conducted to the plate. There is negligible voltage across this winding, and it might be 5 volts or so. So here I've indicated 360, 355 here. The pentode also has a screen grid here, and there are a number of ways that can be controlled, but in this design we're using a resistor, and the conditions at the screen, just like the conditions at the plate, determine how the pentode performs, so we have to take some care with that in the design. In this particular design, we're using a grounded cathode design. Like a MOSFET, where the voltage difference between the gate and the source controls the current through the device, the voltage difference between the cathode and the grid in this vacuum tube controls the current. But here's the difference. With a pentode and vacuum tubes in general, the greater the difference, the less the current. The less the difference, the greater the current. A practical way to remember this is that if you lose your bias to a vacuum tube, say this wiper lifts on the pot, and you lose your bias, you're going to burn up your tube. In this design, we're using a type of bias, and it's called fixed bias. It's a bit confusing because fixed bias is almost adjustable through a pot. There's another way of biasing a pentode called cathode bias, and we'll look at that next. This drawing illustrates a typical topography known as cathode bias, and in this example we use a resistor here to elevate the voltage of the cathode a little bit, basically up to the operating point. And let's see, our operating point is 12 volts negative. We use this to raise the cathode to 12 volts positive and hold the grid at ground through a reference to ground anyway, through what's called a grid leak resistor here. And additionally, a capacitor is used right here to provide a better path to ground for the AC, small signal current, to hold that close to ground. You'll also notice here a coupling cap in this grid signal provided from the phase splitter. In this situation, the phase splitter is invariably going to be at a different voltage, usually quite high, DC-wise anyway, and we're trying to hold this grid at 0, so we put in a coupling cap here to block the DC. And you'll notice here that we've set up a high-pass filter. The RC relationship between that capacitor and that resistor is going to determine the break frequency of that high-pass filter. We want to pick a value for this capacitor and resistor combination that will allow us to pass most of the audible frequency. And we specifically do not want to pass frequencies we can't hear, because low frequency amplification will consume a great deal of power, and we don't want to waste that on frequencies we cannot hear. Typically I use 5 to 10 hertz. That's a nice wide band that allows you to pick a value of capacitor and resistor that will work well. In this particular circuit that we're using with this amplifier, I believe that's a 0.22 microfarad, and I believe the grid resistor is about maybe 200K. In order to build some intuition into how a pentode characteristic curve works, I'm going to review the plate characteristics for a small signal triode known as a 12AX7. This is a very common tube used in guitar amplifiers. Here is an example. If you look in there, I think you can see that there are really two devices in there, two triodes. This is a dual triode, and this is the curve for it. Over here I've kind of sketched how it would be drawn schematically with VS up here. We call it B+ often in guitar amplifier applications. And a load resistor, a cathode resistor, cathode, base, plate, voltage in and voltage out. The cathode resistor is used to bias it up to whatever level we're going to need, as determined by these curves here. And the load resistor, of course, will set the angle of the load line, the slope of the load line. So in this application, this is an exaggerated application, or a drawing that I've done just for effect. In truth, you would be using this probably for guitar amplifier, and you'd be taking a very small signal over here, maybe 100 millivolts, and playing up and down the load line here, and producing yourself some gain here that would be something less than 100, but not a lot less than 100. And for doing this, we're going to pick an operating point about right here, a little less than 200 volts, and at the intersection of the 1.5 volt bias line. Let me explain why I'm picking this point. If you'll notice, the distance between this line, this space here, and this space here, and this space here, they're all very, very equal. If you really wanted low distortion, you could certainly operate right here. But this is pretty good too, and it has the advantage of being the same voltage as the forward voltage on an LED. So instead of using a cathode resistor here, at this operating point, we could replace it with an LED. Just makes design a little bit easier. But we could operate here as well. So we know what our B+ is, so that determines a point right here. If we had zero current flowing through here, our B+ value here at the plate would be the same as the plate would be the same as the B+. So you get a point right there. And then we've selected our operating point. We draw the line here, and the slope of this line gives us the load resistor value. It's 360 degrees divided by about 2.25 milliamps, which gives us the 160K that we'd use here. We know that there's going to be about a little less than, well, let's call it about 1.1 milliamps and 1.5 volts. So if we wanted to use a resistor, we could take the 1.5 volts divided by 1.1 milliamp and come up with about 1,360 ohm resistor for this application here if we didn't want to use an LED. Now you can see over here that we've got, I've drawn these lines out like we did in CECC4, and we're swinging them from about 1.5 volts up to a half a volt negative and down to 2.5 volts negative. And then we draw these lines over here and we see the corresponding output wave down here. So in this example, we're going from 190 down to 105 and back up to 270. So we can calculate the gain as being the difference between 270 and 105. You'll see I've written that down wrong. That should be 165 divided by the 2 volts up here. And that will give us a ratio of something like 85, which would be our gain. But what I wanted to illustrate with this example is that this difference is 80 and this difference is 90. You divide those two and that gives you your the difference between these two, actually divided by the whole, gives you the distortion figure, total harmonic distortion. And you can see that we pushed this just a little bit too far. You know, by operating real close here or real close here, we would have much less distortion. Anyway, I wanted to point out how similar this is to a MOSFET. Really, the only difference is that the voltage characteristic here is just opposite. The grid to cathode relationship is just opposite of what it would be in a MOSFET. So now let's use that insight to look at the plate characteristic for a triode. This is for the 6L6GC vacuum tube. Here's an example of one. This is a Chinese tube that I bought real cheap, and looks about like that. Now, from a practical standpoint, we need to pick a B+, an idle current, and a bias voltage, and select a screen current. And in order to do that, we need to pick an operating point. And the characteristic curves are accompanied by some data sheets that offer some suggestions. And you'll notice up here that our rated voltage is expressed down here, and this assumes a screen current of 250 volts. There are different curves for different screen curves, for different screen voltages, and I've picked the 250 for a variety of reasons. One is that our op-amp driver is not going to be able to provide, let's say, 24 volt peak to peak. It's beyond its capability. And I'm thinking 16, 17 is the right number. And if we bias this at 360, we'll have an operating point that is right about the 16 volt negative line. And that will give us, I think, a very workable solution. So here is our load line, and it's set by the transformer and the speaker. I talked about how the reflected load through the transformer from the speaker determines the load-to-load resistance on the plates, and that number was about 3,600. So what I've done is drawn a slope of 3,600 ohms right through that operating point. And so we'll be traveling up and down this as we operate, as this pentode operates. And just as we did in class, I'm going to draw these lines out this way and down this way. And we'll then draw our input and our VI and our Vout waveform. Now, we'll be traveling up this load line all the way up to about right here where we run out of curve. And this will correspond to about the -4, and this will correspond to about the -16.5. And therefore, we're going to have about a 25 volt peak-to-peak waveform here. Now, because this is a pentode used in push-pull, it's only going to conduct on the positive waveform here. So we draw the line down this way, and we ignore the back side here. That's kind of a good thing, because you notice this looks pretty evenly spaced through here, and that should give us a nice undistorted sound. As you get this way, they become more compressed, and that is another reason that we don't operate at 450. We could operate at 450. I've even drawn a point there. We can also operate here at 250 and get even less distortion. And of course, if we did operate at 250, we'd be using a 12 volt negative to say, well, again, it'd be about the same point on the operating line up here somewhere. So we couldn't go much less than 4. And but again, a very workable option. So to have a look at our gain here with a negative 12 difference between here, or rather 12 and a half of that 25 volt peak to peak that I spoke of, and here going from 360 volts all the way to 30, back again, that gives us 330 over 12 and a half for a negative 24 on our gain. So, to summarize, we've picked a B plus value of 360, and that's what we'll set our power supply at. The idle current is going to be read across here, and that's going to be about 62.5 milliamps, and that will be how we set our bias. We'll adjust our bias on our power supply to bring it up to that voltage, and we should see a correspondence between that 16.5 and the actual voltage that we supply. Certainly with a perfect tube we would have that. With this tube, maybe less so. My guess is we're going to need a little extra bias, but we'll see. Next we have to set screen current, and we'll use a different curve for that. Well, actually we could use a screen current. We could just use the data page, and it gives us exactly what we need to know. We've picked 360 volts for our plate voltage, and our screen voltage we hope to get around 270. And in order to do that, we're going to need to set pick a resistor value. And in this case, we're looking for 5 milliamps to the screen. So the difference in voltage is about 90, and we're looking at 5 milliamps per tube. So back to this drawing, we have 355 volts here, or 360 here. Yeah, 360 here, and we've got about 250, or actually 270 we learned from the data sheet. So we're going to need to set this resistor value right here in order to give us, and here as well, in order to give us the correct current to that tube, to that screen. So here we have 90 volts divided by 5 milliamps. So if we want to size those resistors, we would use 18K basically for each one. Or if we want to just use one resistor and supply them both, it's not as good a design, but in this particular situation it's already set up that way. So what we're going to do is use a common resistor, and it'll be sized for something like 18K. Or rather 9K, actually. I believe we're using a 10K resistor, truthfully. So now let's summarize what we know so far. We've picked an operating point here, so we know our B plus is going to be 360. And we're going to expect about 355 on the plate. And we've decided that we're going to run the screen at 270, and that's about 5 milliamps a piece, so we've sized our resistor. We have picked an operating bias voltage of negative 16.5, so we'll set that on both here and here. And we've determined that we need about a 25 volt peak-to-peak signal in order to drive this, so we'll design our driver circuit to output that voltage. So we're going to have 25 peak-to-peak here, and over here we're going to have about 660 peak-to-peak, and that's going to be reduced through this transformer, and it'll come out to about 32 peak-to-peak at the speaker. It's interesting to note that there isn't much voltage gain through this stage. We start at 25 volts and we end up at 32 volts. But what we have done is we have built a power amplifier. Our power amplification has increased greatly. This signal basically has no ability to produce any power to speak of, whereas this can produce about 47 watts. When we eventually test this, we'll compare this signal to this signal and see how close we match that. Let me make one other comment here. In Chapter 8, when we discussed differential amplifiers, the subject of common mode noise rejection came up, and that is one of the strong advantages to using a push-pull design is that any noise that might remain in the form of ripple in our B plus power supply will be introduced equally to both vacuum tubes, and will be then that effect will cancel itself across the transformer. So we don't have to spend a lot of effort or money buying capacitors to filter our B plus. Okay, now that we have all the preliminaries out of the way, we're ready to have a look at the driver circuit, the subject of this 6002X adventure. So we know that we need 25 volts peak to peak from the driver, and that we need two outputs out of phase with one another. And we know that we're going to design for an input from an iPad or an iPhone or an iPod. And those outputs are generally about 1 volt RMS. It does make a difference what you're designing for. A CD player will have about twice that, about 2 volt RMS. A tuner, about half that, maybe at a half a volt RMS. Phono stage is a whole other matter. It'll have maybe 100 milliamps, and it'll need an RIAA filter circuit to go with it. These circuits are very inexpensive, and it wouldn't be any big deal to design one for each input on an amplifier so that everything would be nice and level. Just an observation. Anyway, so we're going to start out with 2.8 volts peak to peak and end up with 25 volts. So we know what gain we're trying to get to. So our gain is 25 over 2.8, or about 9. So I've selected a 33 k ohm resistor and a 2.2 k ohm resistor to give me about 15. The reason I'm doing this is twofold. It's been my observation that this op amp, which is a LM4562, doesn't really live up to the R1 over R2 amplification expectation, and maybe coming in at about 3/4 of that. The other thing is that too much gain isn't horrible, because we can simply not turn up the volume all the way on our source, and too little is a problem, because then we don't fully drive our output stage and we don't get the power output that we would like to get. So better err on the high side. So what we're going to do is come out of here with our source signal, and we'll first amplify it in this stage here and output that to one of the coupling caps on the pentode. And then we'll take that amplified signal and invert it once again back the way we found it, and we'll use a 33 and 33 R1 R2 situation here so that we have no amplification. We get gain of 1. And that should accomplish what we need. There would be other ways to do this. You could simply use two different op amps and have them both amplifying, and one inverting and one not. But I would be a little concerned that perhaps one signal might be a little greater than the other. And then there is an overall problem of needing to sum back in our negative feedback. And to me it makes sense to take our negative feedback and sum it in to begin with, and then we know that it is appearing in equal quantities in both waveforms. I note that this is a hi-fi concern, because we want to keep distortion down as low as possible. In a guitar amp, it might be interesting to monkey around with putting negative feedback only in only on one wave to see if we can create some interesting distortion, but that would be another project. So overall, our global gain around the amplifier is going to be about 33 volts across the speaker terminals, divided by the 2.8 we're putting in here. That should be 2.8, and that gives us a global gain of about 12. And feedback is usually the reciprocal of that, so a global feedback of 0.083 or 8% would be a common number. And to get that, we'll take 0.083 times 22K, which happens to be the feedback resistor value, and we'll divide that with a voltage divider by 1.8K to get this small signal that we need, and we'll introduce that to the plus terminal of our op amp, and that should introduce that and work just fine. Now feedback's kind of a funny thing. We need feedback to keep the amplifier from oscillating, but feedback reduces gain, and it also tends to overdamp an amplifier. So sometimes you get better sounds by using less than full feedback. So it would be my tendency to start with a low number, maybe half that value, and then work up to the full value if it's needed. If it doesn't oscillate at say 800 ohms, then I wouldn't be concerned. There's a lot of negative feedback that gets into the amplifier along the way in unpredictable ways, and so sometimes the full feedback isn't required. I mentioned that I'm using an LM4562, and this is what that looks like. It's on one chip. We have two op amps, and you can see V plus here and V minus here, and outputs and inputs and so forth. This particular op amp I selected just because it was in the Mauser catalog as being a specifically built for audio purpose and marketed as a low noise op amp, which seems to be very desirable. It has a limit of 36 volts supply voltage, so you're not going to get more drive than say 34 out of this thing. So if you were trying to drive a high-powered triode, it wouldn't quite go for that. There are some interesting circuits you can use to get more out than this, but that would be another subject. So let's have a look at the breadboarded power supply driver circuit. Here we have our op amp here, and like I say, it contains both. It contains two op amps, both that we need in the circuit. Here's our R1 and R2 resistor for the first one, and here is our two 33K resistors for the second. Over here I'm using a rail splitter to give me the 0 volt, and then I'm using a power supply supplying the difference between the 36 volt differential there. These are my input leads from the source, and here is the output to the amplifier, and here is my feedback, and here is my feedback resistor there. Okay, so we have the driver board hooked up now to the oscilloscope and a function generator. The function generator is set on 1000 hertz, and I'm putting out a signal that's about 2/3 of our expected range of 1 volt RMS, and you can see that we're getting a amplified signal here. This is set on the 10 ohms. Pardon me, the 10 volt scale, and we're showing something here about, well, that doesn't help a bit. We're showing a little over 20 volts here, and to get the exact numbers I'm going to use a RMS voltmeter. So can you focus on this here? Alright, our inlet voltage is about 0.68, and our output voltage is 9.3. So 9.3 and our 0.68 divide is about 13.6 gain. So we're not quite getting 15 gain, but it's pretty close. My comment about R1, R2 was a bit exaggerated. So let's see what our waveforms look like. There's sine wave, and there is a sawtooth wave, and there's a square wave. We're not seeing any overshoot on the square wave, no oscillation, and that sawtooth form is very nice. It looks like it's very much undistorted. So we're real happy about that. Okay, now I've changed my probes around, and I've got both scales set on 10 volts, and we're looking at the two outputs with, we desire to have 180 degrees out of phase, and you can see that they are. And also you can see that they're pretty close to the same amplitude, which is what we wanted. And let's have another look here. Yeah, isn't that nice? It looks like so far we've been very successful. Now I've hooked the leads up again a little differently, kind of like it was in the first time, and we're going to look at the point at which we start clipping and saturate. And I'm going to start turning up our gain here to the point where we start clipping. Let me go down this way. Bring it up. We get to the maximum of that scale without any clipping. So then I change to the next, and you can see just right there it just starts to clip. So let's see where we are in the, with voltage. You can put it back over here again. We're at about 2/3, about where we were the first time. So basically what we're saying is that when we turn our volume control up on our source to about 2/3, we're going to get the full drive and begin saturating and clipping. So we have, as we thought we would, too much gain, and there wouldn't be any problem with reducing that gain some. In a guitar fire application, you want to be able to overdrive, but you probably don't want that in a hi-fi. So either a little discipline with the volume control or a little less gain. Either one would work nicely. In the next segment, we're going to fire up the vacuum tube amplifier and run it with this and see how it sounds, see how it looks on this scope. Okay, so here's the vacuum tube half of the amplifier. This is something that was salvaged from an old organ, I think a Lowry organ, and I'm just using the tube sockets and a couple of resistors and this output transformer. I like having it all in a nice little metal enclosure to keep all the high voltage components here with lethal voltage is safe, so we don't have it all strewn all over the place. And of course these voltages are low, so everything here is low voltage. And we're going to start this up using this power supply here. And we can use this to adjust the B+ voltage to any value we want. And we can monitor our bias current on this meter and adjust it with this bias here. Here's our B+, our neutral. Here's our bias output. And here is the 6.2 volts that go to the tubes for tube heaters. So here we go.
I don't know if I was...
Okay, I want to show you the underneath side of the amplifier. Here are our tube sockets for those 6L6 GCs. Here are the coupling caps. Here's the bias network with its two resistors and feeding back to the power supply. And here's our screen resistor down here. Our B+ ties here, and it goes to the transformer, center tap, and then from out of that it goes to both plates. And over here from B+, we go through this resistor that I've assigned to use as a screen resistor, and then back over here to the screens. So we're going to operate this at several different operating points. The first operating point I'm going to select is at 250 and about 72 milliamps, and that should give us around -14 on the bias. So to do that, we're going to start dialing up the voltage here. Bring this up to about 250. Well, I'll bring it back down because I forgot to do something. What I want to do is to put these leads across that screen resistor so that I get the equal voltage, get 250 both to the screen and to the plate. So we'll just use this. Alright, now we're ready to go. Now I'm going to adjust the bias to give us a little bit more power. This is supposed to operate around 140. We'll be happy with 125. And let's turn this down a bit. So I think we've seen from our previous deal that just about any value I select here will not saturate my driver stage. But you can see that we're pushing the amplifier into clipping here at the 250 point quite early. That that's probably at the 12 o'clock position here, the 1 o'clock position here, something like that. So let's see where we clip from a voltage standpoint. Okay, AC, volts, and that's about 7 volts here. And that's where our clipping begins. So I'm going to bring this back down again. And we'll just pull these off. Now we're going to go for our operating point here, which is about 360 volts and about 16 negative on the bias, and we're going to use our screen resistor as is. Watch up here. You can see the as I bring up the power, we're starting to get a waveform. And over here, we're going to go for 360. And by the way, we can measure our bias here. We were expecting 16, and we're getting way over 20. Now that has more to do with the tube quality. The tube is not riding exactly on its characteristic curve, which isn't too surprising for a economy tube. And I want this to run at about 90 milliamps. Let's see if that made a difference. Brought it down a little bit. So let's see, we're not in clipping yet, and you can see we can go further now before we reach clipping. As a matter of fact, I've got it fully up. So at this point, we're getting the full driver voltage here, and we're seeing it coming out here without any seeming distortion. Let's go to that wave. See, it all looks pretty good. And let's measure voltage here now. Now we're getting 9.1 volts, which is pretty close to our expectation. So that voltage was about 25 volt peak to peak. Let's see if we can go further. Now you can see I'm starting to clip here, and it's inverted, so we're clipping here. And that's to be expected because our driver is clipping, our output has got to be clipping too. So let's kill that off and go to the next higher stage, operating point. Okay, before we go on to the next operating point, let's look at our data and make sense of what we collected in this first operating point. We had a VN of about 9.85 RMS, or 27.8 peak to peak, a V out of about 26 peak to peak, and we're using 90 milliamps of current. It took 22.5 on the bias. Our B plus is still 360, and our screen grid's at 265. So let's have a look at that on this chart. Now, here is this operating point that we are using, and I'm going to put a load line along here. It's parallel to the other one because we haven't changed the transformer, obviously, and we're going to be moving up and down this line. Now, I said we had about 28 peak to peak, which gives us 14 peak to move up and down this load line. Now, this should be at negative 20, and 14 should move us to about 6, which ought to do the trick, which should give us the voltage we expect. But there's one problem. Our tube is not really operating at negative 20 bias. It's down here somewhere. So we're running out of drive. That would be voltage from our op amp before we get to the top here. We're losing steam over here somewhere, so we're not developing this full waveform. And as I adjust to the next operating point up here, we'll see how that changes. So let's have a look at this. I'm going to leave it at 360, but I'm going to reduce the bias, and I'm going to bring it down to that 16.5 number that we thought we would need, and see where that brings us over here. Oh, this is interesting. We're only getting about 110 milliamps, and that's not quite there yet. So our bias error has gone the opposite direction now, which is just means the tubes really aren't riding on their operating curve. You get what you pay for, right? Okay, so now my bias is all the way down to negative 13, it looks like to me. So let's write that down. Negative 13, 360 on the B plus, we're 125 on the current, and we are, let's look at this here. We're exactly, well, let's say 11.05 on the out, voltage out. That's being measured at the speaker, by the way. And our voltage in is still 9.85. We haven't changed that. So we're still 27.8. And you can see here from our waveform, the top one is our input wave, and you can see that the bottom one is clipping. So at this point, we are getting clear to the end of our operating line. So it's time to turn down our VN just a little bit and get one more point. Ooh, we got to go way down. Okay. Something like that maybe. Looks better on the sine wave, doesn't it? Okay. So, let's have a look at our operating curve again. I'm going to turn this down. I don't trust those tubes working at that point. There we go. Okay, let's have another look at our operating point here. I said 11.05. So that's 31.25. So we did get very close to the voltage that we had predicted. 33 was the number we had expected to see, but this was with quite a bit of clipping. But let's look where we are anyway. So we moved up to this point, and we aren't really at 16.5, were we? We were at, what did I say? Negative 13. So we were with our bias, with our drive going at 14, we were overshooting here, and that's why we were clipping. So let's see, what does that mean? If we were playing a music source, we would be obviously turning it down some. We're getting our full range here, and the number that I didn't get that I would like to have would be our VN number after I turned it down to stop the clipping. So let's go back over here and do this one more time. Let's bring our bias back down, and there's our 125, and our bias is, oh, look at that, our bias is back up to 16 again. Isn't that something? The tubes aren't acting totally consistent, but in fairness, they're warming up. So let's draw another line here. Let's go back up and have a look at this too. It seems to have gotten well here while we were away. Let's see, I was up here. Yeah, we're still getting a little clipping. It's not as bad as it was. Okay, we'll use that number. So we have over here on our V out, we're back to 9.75 without clipping. And let's measure our V in. Let's see, turn the light off real quick and you can see it up here. We're right at 10, it looks like, maybe 9 point. Let's just measure it. Don't need to guess. 8.28, so 8.3. Okay. So our tubes haven't melted down yet. Let's go for one more operating point. Okay, for this next operating point, we want to pick something that's pretty close to 100%. This last point was at 70% of power. I have drawn the 100% curve along here. This is what the maximum rating would look like if it were printed on that plate characteristic. Here's a plate characteristic for an EL84, and you can see that they've actually drawn the 12-watt plate dissipation curve on here. And so this is our 30-watt plate dissipation curve here. And I don't think I really want to push those tubes that far. that would be 82.5, but let's go up to 80 and just for a moment and see how they behave. And we should expect a very low bias number, and of course our drive is going to way overrun this, so I'm going to go ahead and just turn it down right now a little bit. We can see, yeah, that's probably going to be close. And let's get some numbers on this. So we're looking at 8, that's 160 for the pair. So we're going to bring this up. $160, and our bias number is at 11. Okay, bias is 11, and V out is not being measured at the moment. Let's check it out. Okay, let's go ahead and turn this up till we get some clipping. Looks like we're starting to already get clipping. Yep. So we're still at about 9 volts. V out, and our V in, when we're getting 9 volts, is 6.3. Okay, let's see if we got any color. Back up a little bit and see if we're getting any red plating going on those tubes. Right down there. Yeah. No, there's really no sign of any overheating. Let's cook them. Let's go up a little more. Let's get over the 100% number. There we are. See if we get any red glow. They seem to be alright. I think we'd have to go a little higher than that. Why torture them? So I'm going to turn it back down a little bit and let's have a quick look at our numbers. If we don't cook it, then we can listen to it. Okay, so we were all the way down to VN of 6.3. Or about 17 volts peak to peak. So it took from 11 here, we were running up this curve way up here, and of course we're still getting the same peak to peak output really, because our voltage hasn't changed much. In other words, we're running our tubes a whole lot harder and really not getting much out of it. And I have a few thoughts on that, but let me think about it for a moment and see if I can come up with something sensible. Okay, now we're hooked up to my iPad, I believe. Yes, we are. And I've got it set up again at 360 volts and 125 milliamps, and this time we need a bias of 19.5. So these tubes are not being very consistent from one use to the next. Perhaps getting them really hot on that last trial has permanently or temporarily changed their operating, their transfer function. Don't know. I suspect that the next time around they would come right back where they were. They're probably just at a different temperature now, but we don't know. So I'm going to start the iPad here, and I want to let you look at something here. Our initial assumption was that we would be dealing with a 1 volt RMS output from the iPod, and that we would, we would be amplifying it accordingly. And a full scale on this thing is about 2 volts RMS. This is, I've got it set on the 1 volt per division, so 6 divisions, it's about 2.12 volts RMS. And I'm just going to crank it up just for a moment. What we're seeing here is a real strong bass line with some banjo riding on it. And so there's a So what we conclude from that is that our amplitude is probably close to 6 volts peak to peak, 2 volt RMS, not 1 like we had initially assumed. So we have loads of gain. Now let's look at the output real quick. Let's see, I'm going to move this up a little bit and bring the output up where we can see it. And we'll just do the same thing. Well, that's all well and good. You really can't tell much from that, but you know, it looks to be doing fine. It sounds really good. It's got real fast bass, real tight. The banjo sounds real nice. It really rings beautifully and has a nice jangly sound. It's I was prepared not to like this because after all we spent what $5 building this thing, and it just sounds wonderful, and it replaced a whole handful of tubes. So I am pretty pleased with it. Now, as regards our lack of increasing amplitude when we went up to a higher current on this our operating point, I think the reason that we didn't get any additional amplitude is simply that we were getting all the amplitude that we could get at a lower power rating. And if we wanted more amplitude, we'd need to add more volts and go this way, so we'd have a larger waveform. If we were operating at 450, for instance, instead of 360, we'd be getting a taller waveform, and we should be producing more power as well at the speaker, as measured as V squared over R. That's my thoughts on it anyway. Now I'm going to play this again just for a second, and let's see, there we go. I'm going to turn it up. Okay, that's full volume there, and we're really not having a problem that I can hear with any clipping or a horrible distortion that's audible anyway. This really sounds good. I guess it's a kind of, me telling you this sounds good and showing you a picture of it, it's kind of like me showing you a picture of food and saying, see how good it tastes. It's recorded on a cheap microphone, and you're probably listening to it on a laptop, but I'm real happy with it. So I think that'll conclude our presentation. We determined that the op amp is able to provide the right amount of gain without any problems for a 6L6, and it's one of the more difficult tubes to drive. It should have very little trouble driving an EL84 or a EL34, and it would be just a resistor change away to change the gain on this. So if we decided we wanted more gain or even less gain, it would not be a problem. And especially for a guitar amplifier application where we're going to be operating at maybe 100 millivolts, a much smaller signal, we'll want to add some gain. And we'll talk about that more in extra innings, but I've taken enough of your time for now. Thanks for listening to my presentation. Okay, everyone, we have here Bill Tanner, the lead guitarist for John Denver's Head, who's going to help us test out this amplifier. Go ahead, Bill.
Oh, you did fine. Thank you, Bill.
That's all
all you need.
We just heard Bill play our guitar amplifier, and this is the breadboarded driver circuit, our amplifier and concertina phase splitter. We added one gain stage to this in order to get the additional gain that we're going to need for a guitar amplifier, because we're starting at about 0.1 volt and going all the way up to 33. So instead of our nominal mid-teens gain that we had for the hi-fi model, this one's got a gain of about 330, so we had to go with one extra op amp, and we've added a pot as well. You'll notice a couple of capacitors I added because I blew up my rail splitter somewhere along the line. All the smoke got out of it, and we had to go to another plan, but otherwise it's quite similar. With the hi-fi version of this amplifier, I was really impressed by how incredibly quiet it was. With a tube amplifier, it's not uncommon to have a little bit of hum that's audible from an inch away from the speaker. That's caused by ripple that's on the B+ that gets carried through to the first stages of amplification, which are done Class A. The ripple that appears on the plate gets carried through to the amplified signal, and it's really hard to get rid of that without using just a whole lot of capacitance. And with this, it was very, very quiet. This circuit, on the other hand, picked up a lot of AM radio. With these resistor leads standing high like they are and untrimmed, we were getting a little bit of interference, and you could see it on the oscilloscope too. In order to make this circuit good, and with any circuit dealing with a lot of amplification such as phono stages, it's real important to get those resistors trimmed and your components placed so that the resistor leads are real short, because each one of those guys acts as an antenna. Kind of interesting. This drawing represents the breadboarded circuit. You'll recognize this much of it as being basically just the hi-fi version, with the 2.2K resistor and the 33 for our gain, and then the 33 by 33 inverter to give us the concertina phase splitter. You'll notice that the feedback resistor in the voltage divider has been changed. Our gain on the hi-fi version was in the mid-teens, and here we have 330, so it's basically 20 times greater, and we've had to make an adjustment to the voltage divider. The feedback formula, I should say the feedback formula is 1 over the gain, so our number would be 0.003. So we'll use that to calculate the value for our voltage divider. 68 divided by 22K. And of course that is summed back into this op amp there. And of course you'll recognize this from the textbook study of subtractors. Anything that we feed into here would be subtracted from this signal. And from this point over, what we've had to do is to add a gain stage, because our guitar amplifier pickup is putting out about 1/10 of a volt. So we're going to have to take this and raise it up to the level it was coming from our iPod. The topology of this circuit is very common, and you'll find it in guitar amplifier diagrams going back to the 40s from Fender and Silvertone and Marshall, and if you were to go buy a guitar amplifier today, you'd probably see the same circuitry. And this position here would normally be a triode, a vacuum tube triode like a 12AX7. And this pot here and this one here serve an interesting purpose. Our voltage coming from the guitar pickup can be fed at a low level or a high level across this first triode in order to drive it very hard or well within saturation. And then this pot here then can be used as control of the volume, so that when the signal is sent on to the power amplifier stage, it can be sent either clean or distorted. And if you wanted to have a real highly distorted sound, you turn this pot way up, overdrive this vacuum tube, and then turn this one down to keep the rest of the amplification within saturation. If you were George Benson and you wanted a very clean sound, you would run them both within saturation and keep the signal clean all the way through. If you were wanting to achieve a very highly distorted sound, then you could adjust these controls to your liking to create either create your distortion in this stage or create it in the power amplifier, because they're going to sound quite a bit different. A Class A vacuum tube operated really hard is going to create a lot of even order harmonics that have a characteristic sound, and the odd order harmonics created in the push-pull stage are going to have a whole different sound, and guys use that to, you know, craft their own sound. Bill's a blues guitarist. He plays Howling Wolf and Muddy Waters to say Clapton and Led Zeppelin, and so he likes his sound reasonably clean, and he has his fun with feedback. And so I set this up on the scope to run a signal at about 0.1 millivolts, and made sure that it was nice and clean, and it sounded really good. I did try this in a range of distortion, both clipping this and then this alternately, and you know, it really didn't sound that good. It didn't sound like a vacuum tube triode at all. It just sounded like clipping, and I can't really recommend it too highly, but you know, it did work. And I'll note that stomp boxes and lots of effects devices use solid-state components, so I know that it can be done. It's just that this particular circuit isn't too interesting for that type of overdriven sound. I did try a couple other things. Instead of putting the pot here, I put a pot up here, and I tried to use outrageous amounts of gain to overdrive this circuit, and it really didn't work very well. It didn't sound particularly interesting, and in the end, I think the pot placed here really does better. That kind of surprised me. I really had high hopes for overdriving that, and I may try it again sometime with a little bit more wasn't too impressed with it. I have just one last footnote to add to those who are interested in the triode discussion. That discussion went quite long, and I decided not to include this little bit, but I'll include it here now for those who have some interest. This is the 12AX7 curve, and I'm going to zoom in on it a little bit and try to show you something that you can do with solid states or with vacuum tubes, either one, to make this tube just a little bit more useful. There are some very interesting applications in vacuum tube circuitry for audio that requires that you run clear up and down the operating line. And we learned in class that the idea was to operate on a very small portion so that it's linear. But in some circumstances, like designing for very large triodes like this baby, you can see it's the size of a sheet of paper. The swing that we need to drive the grid is something like 400 volts. Now, how are you going to do that? Well, you could draw a load line from, say, 500 volts, use that, and put your operating point up here somewhere and run up and down this. But it's going to be kind of a problem, because you can see these lines get closer and closer and closer together, and by the time you're down here, it's not good. So let's say you biased halfway, but at 2.5, you would swing from here to here and from here to here, and your sine wave would be very asymmetrical, and you'd have some really horrible distortion. But look what happens if you were to draw a horizontal load line. All of a sudden, that problem just goes away, and you can run from 50 volts clear out to 400 volts, and all those gaps are all just about equal. And from here you can see you can run from say 2.5 volts at about 250, clear out to 400 plus, and clear back to about 50. And it gives you a much linear application. And the way you can do this is by using a MOSFET or another vacuum tube to replace the load resistor. And when you do that, your operating point falls. It falls at the intersection of your bias that's applied, say 2 or 2.5, and that current that you select. So if you selected, let's say 1 milliamp, and you selected 2, your operating point would be right here, and that would be controlled. Your operating line would be here, and your current would be controlled by your, well, it could be a MOSFET or another vacuum tube. You'd simply bias that and set it up in the in place of the load resistor right here. Something to think about. I'm going to build a driver circuit for that vacuum tube that I just showed you, and I intend to do it that way. And I'm still trying to decide whether I want to use a vacuum tube or a MOSFET on it. But these things are said to sound really nice. It has 1,000 volt plate voltage, so it'll be an interesting project. Here is the plate curve for that 845 that I was telling you about. I have to confess to a bit of exaggeration. I think I said 400 volts. 300 is plenty. 280 is plenty. We are going to be operating here at about 1,000 volts and about 90 milliamps. And we'll be operating up and down this curve just like this. You see how linear each of these spacings are here? Should be really nice between 300 and 0. And operating right around here should be a real nice operating point. And the point is that this can only be accomplished with a constant current source. Well, I hope you enjoyed 6002X as much as I did. I'd like to thank Professor Argawal and everyone else at 6002X and EDX for putting together this wonderful opportunity. And if you haven't seen Professor Argawal's presentation on the TED Talks, you ought to look at that. That's pretty good too.